Let us start this lecture with a thought process by great scientist and Nobel laureate of modern India, Sir C.V. Raman, who says, ask the right questions and nature will open doors to her secrets. This is a very profound statement that is embedded in our mind from time immemorial. As a result, our science and technology based on the philosophy of India is quite eco-friendly as compared to the western science and technology. And let us recall what we learnt in the last lecture. In the last lecture, we discussed about hybrid propellant rocket engine, covering most of the aspects in a very brief manner and looking at how it is different from the other two rocket engines, solid propellant and then liquid propellant rocket engines, and how to calculate the regression rate and what is the performance parameters and other things. And in this course, entire gamut of chemical rocket engine have been covered till now, but today we will be discussing about non-chemical rocket engine. As the name indicates that in case of non-chemical rocket engine, the energy source apart from the chemical one will be used for propelling the rocket engine. And based on the type of non-chemical energy sources, we can classify the rocket engine into three categories for our discussion purposes, and those are electrical rocket engine, nuclear rocket engine and solar rocket engine. Keep in mind that we had discussed earlier that there are other forms of energy that can be utilized. Let us now discuss about electrical rocket engine, in which the electrical energy will be utilized for producing the thrust using the rocket engine. When we talk about the electrical energy source, that can be of two kinds, and one is the thermal energy that can be produced with the help of electrical energy. Other one is that one can produces arc and then do that. Before discussing about it further, let us now look at what are the differences between the chemical and non-chemical rocket engine. If you recall that chemical rocket engine is energy limited due to the fact that chemical energy is release is being limited, and as a result you cannot have a higher ISP, and if you recall we can have specific impulse by using the chemical energy in the range of something 180 to maybe 465 seconds. In contrast, in case of non-chemical propulsive system, power is limited due to the limited energy conversion rate, and there is another constraint, that is the material which can withstand high temperature, because in case of non-chemical propulsive device, the temperature of the gases or the medium which will be much higher level. And beside this, like in case of chemical propulsive device, the payload fraction is quite low, and in non-chemical propulsive device the payload fraction will be higher, because it is having a separate power source, and the chemical rocket engine can have a very strong burn rate, but for a very limited, very shorter times. As a result, we can get a very higher thrust level, but for a shorter duration. In contrast, in case of non-chemical propulsive device, higher energy content to be supplied to the propellant. Therefore, we can have a very long duration, but due to the power limitation, we cannot have a very strong energy conversion rate or higher energy conversion rate. In case of chemical propulsive device, the high thrust can be produced as the propellant mass consumption is quite high, whereas in case of non-chemical rocket engine, high specific impulse is being produced with high exit velocity and with low propellant consumption rate. And in case of chemical propulsion, very moderate exit velocity range can be achieved. In contrast, in non-chemical rocket engine, higher exit velocity, but with a low thrust level and acceleration can be achieved. And as a result, in case of chemical propulsive device, limited final velocity can be obtained. In contrast, very high final velocity can be achieved in case of non-chemical rocket engines, but with a very low thrust level in the range of 0.005 to 10 Newton. Hence, it is not useful for the application on the planet surface, where gravity playing a more important role. In contrast, in case of chemical rocket engine, very high thrust level can be obtained. Hence, it can be used very much for the near earth regions. However, the non-chemical rocket engine is being preferred in the space application, where thrust requirement is not high, but however, the specific impulse will be much higher as compared to chemical propulsive device. Let us now look at the electrical rocket engine, in which the electrical energy is being utilized for the propelling the rocket engines. How this electrical energy can be utilized? It is divided into three categories. One is electrothermal rocket engine, and electrostatic rocket engine, and electromagnetic rocket engine. In case of electrothermal rocket engine, basically the electrical energy is being utilized to transfer the heat being generated by the electrical energy to the propellant for propelling or for obtaining the thrust by expanding the gas in a typical rocket nozzle. And electrothermal rocket engine again divided into two categories. One is the Regenerative Jet Engine, other is arc jet engine. In case of Regenerative Jet Engine, the resistance is being used as a result that the electrical energy is converted into thermal energy, and we can also divide into four categories based on the how these resistance were being designed, but there might be several different types of Regenerative Jet engines, and we will be discussing about straight coil wear Regenerative Jet engine, which is shown in this figure. If you look at this, is basically the resistance wear, and this is connected to the power supply, and the propellant is passing through this, and then it will be coming in contact with this resistance, which will be giving the thermal energy. And of course, in this case the heat transfer from this wear straight coil wear to the fluid is a very challenging one, important one, and it may not be very uniform. Therefore, people have used basically another one, that is known as transverse coil wear, where not only in the transverse direction, but the perpendicular to in the radial direction also the coil being placed such that more uniform thermal distribution can be achieved at the inlet of the nozzle. This is your nozzle, and once this is being done, then one can expand this high temperature and pressure gas in the nozzle to get the thrust. But in both the cases, if you look at the structural rigidity is one important thing, and also the higher load it may not take due to the flimsy nature of this coil. Of course, various kinds of coil one can design, one can think of, but in order to improve this better distribution of heat and more amount of heat being transferred to the fluid, then another one is being designed, that is known as spear bed design. In this case, generally the tungsten spears which can withstand high temperature are being packed, and through which the propellant has to pass through, the heat transfer will be improved further. And but problem with this is that it will be having a larger pressure loss and also the radiation heat losses, and it will be bulky in nature. However, one can get the higher thrust because more amount of heat and electrical energy can be converted and to thermal energy, and that can be transferred being used to heat up the propellant. However, these are the limitations. In order to overcome these pressure losses and keeping the other advantages over that, people have come up with a chamber wall. So, this is basically a chamber wall, a concentric chambers which is connected with the power supply or the voltage, and then the pressure losses will be reduced as compared to the spear bed. However, it is much higher as compared to transverse coil and the straight coil. And in this case, of course, the radiation losses will be occurring to some extent. However, it will be much less as compared to the spear head. Of course, there are several other design one can think of. In this case, the specific impulse range what can be used is basically something 200 to 300, and the propellants can be used are hydrogen, nitrogen, ammonia, methane, hydrogen, and any other propellants. But among all these things, hydrogen is being preferred over others because of fact that it is having a higher thermal diffusivity, so that heat transfer rate will be much higher. And as I told, the specific impulse will be in the range of 200 to 550 second, and there will be lot of losses, and these losses are caused due to the ohmic resistance, stray current, and heat losses from the rocket engine, and non-uniform heating that I had already discussed. And beside this, non-axial flow component in the nozzle. If you look at this, will be non-axial component, and that really reduces the thrust level as in case of chemical rocket engine. And let us now look at how to overcome the radiation losses from the engine. Now, a typical practical regenerative resistor jet engine has been designed, and then people are looking at that, and this schematic of this regenerative resistor jet engine shown here. If you look at propellant is coming from the tank and through a valve, controlling valve, and it has to pass through that. And if you look at this is having a 2 radiation shield, and these are basically the electrical heaters, and this will be heating, and then propellant will be coming through that, it will be passing through this, so that it will uniformly passes into these holes through the heater, and this radiation shield will be helpful for arresting the heat losses due to radiation, and it will be re-radiating this propellant. Beside this, some of the heat which will be transferred due to the convection can be regenerated basically by this, by using this radiative shield, and also the propellant is convecting some of the heats into the system. And generally, the tungsten and platinum metal are being used as a heater, so that high temperature can be achieved. And keep in mind that whatever the analysis we had done for the chemical rocket engine can be utilized here. For example, ISP can be related to C star. C star is your characteristic velocity, Cf is your thrust coefficient, and G is the gravity at the sea level. And C star we know that it is basically given in this expression, which is a function of temperature and molecular weight of the gas, and gamma is your specific heat ratio. And of course, the CF you can obtain with using the similar expression what we had discussed earlier for chemical rocket engine. And we can also find out a thermal efficiency. This is thermal efficiency, which is the ratio of the kinetic energy, that is m dot V e square, this is your V e exit velocity from the nozzle, divided by P j. P is the power being supplied to the electrical energy, or and that is nothing but your voltage, and this is your current. And then you can express this m dot V is nothing but your basically F, and V e is nothing but ISP into you can get this expression very easily, and you can evaluate how good or how bad it is, then only thermal efficiency should be high. And let us look at now arc jet engine. In this case, the high voltage is being supplied between the cathode and anode, such that the temperature of arc will be very high and there will be heat transfer, and then it will be expanded in a nozzle, CD nozzle, for getting the thrust. Let us look at a schematic of a typical arc jet engine. And in this case, the propellant which is being used is basically hydrogen, helium, argon, neon, nitrogen, ammonia, and hydrogen, several of them, and one can use basically maybe hydrogen because of it is having a good thermal properties. So, when the high EMF and being applied between this cathode and this anode, anode is the CD nozzle itself, and which will be made of very good high temperature material like tungsten and other thing. So, when it will be applied, and then this propellant will be passing through that, and as a result, due to the very high voltage, that gas will be subjected to ionization and will be broken down and forming a arc column, and this in the inside this arc column temperature will be very high temperature will be there, and this temperature now the heated will be basically transferred to this fluid which will be passing through that. And when the high rate of current is being used and this arc is broken down, and which must be avoided, and that is known as pinching or wiggling up, and it may be moving on the divergent portion of this nozzle, and which must be avoided because it will be reducing the efficiency of this arc jet engine. And hence this is very important one, and if you look at, we can get the specific impulse in the range of 300 to 1550 second, because of fact that this is velocity of 7,500 to 20,000 meter per second can be obtained, because of fact that temperature here what we are getting is very high, something 4,000 to 5,000 Kelvin what we will be getting. And efficiency one can achieve with this arc jet engine is around 30 to 40%, and thrust to power ratio is 6 times higher than that of the Registrojet. Of course, the life of anode and cathode is very important because of high voltage and the erosion will be there. Therefore, its life is limited to something around 800 hours. So, that is why arc jet engine will be giving much higher specific impulse as compared to the Registrojet engines. Now, let us look at electrostatic thruster, and in case of electrostatic thruster, the principle is basically different than what we have discussed for electrothermal rocket engine or the chemical rocket engine. In this case, the propellant is being ionized or being charged, particles are being produced by with the help of electric field, which has to be accelerated with the help of electric field, and which depends on basically on the strength of electric field and charge of the particles and their direction. And if you look at based on how this ionization of the propellant takes place, we can divide this electrostatic thruster into 3 categories, that is electron bombardment thruster, ion contact thruster and collider thruster. In case of electron bombardment thruster, the electron is basically utilized to produce the charged particles, and in case of ion contact thruster, the ions are being produced by coming in contact with the thermal anode, and in case of colloidal thruster, the droplets of the propellants will be charged with the help of electric field and which can be accelerated further to get the thrust. So, we will be discussing about basically a ion thrusters, and let us look at its schematic which is shown here, and it is having 3 component. One is your ionization chamber, this portion is your ionization chamber, there will be accelerating chamber, this portion will be accelerating chamber, right, and there will be this portion will be accelerating chamber. And this is basically ionizer, and this is your neutralizing electric gun. And if you look at whenever this propellant, xenon gas is one of the propellant, of course, the several propellant one can have, as I mentioned earlier, that when this propellant xenon propellant will be passing through this cathode, and also through this is your anode, which is subjected to high voltage, basically cathode and anode, which is not shown here. And whenever it will become whenever the xenon gas will be coming in contact with the ionization chamber at high temperature, because this will be heated high temperature, and it will be converted into the positive and negative particles. This kind of emitters is known as thermionic emitters, and keep in mind that this has to be further being accelerated using the magnetic field with the help of permanent magnetic rings, which is being shown here. These are magnetic rings, and then of course, these particles will be passing through this grid, and there are 2 grids, one is positive, other is negative. The first grid is known as extracting grid, as it extracts the ion particles, because of fact that ion particle being utilized here, whereas the electron particles being lower mass is not being accelerated, not being utilized to produce thrust, and while the second grid accelerates the ion particle to a high velocity because of negative in sign, and that is known as the accelerating grid. So, if you look at this is basically known as the accelerating grid, this is known as accelerating grid, this is the second grid. And then after that these particles will be coming out, the positive and both the negative, then what will happen, that it may affect the performance of the ion thruster. Therefore, the neutralizing electron gun is being used to say that this will be neutralized. And if you look at the propellants, what is being used is hydrogen, krypton, nitrogen, mercury, cesium and xenon. And hydrogen need not to be used, because already it is we need not to have a heat transfer problem here. The krypton and nitrogen is difficult to ionize easily, therefore, this is not being preferred, however, it can be used. And mercury and cesiums are toxic in nature, therefore, it is not preferred very much, and xenon is being used, which is having a heavy in nature, and that is being preferred in case of ion thruster. And for getting higher velocity, higher charge to mass ratio to be used with higher voltage difference, and the voltage limitation of this thruster is that 50,000 volt, and electrical field strength of 10 power to 7 volt per meter can be utilized, that is the maximum one, and the specific impulse in case of ion thruster can be 2000 to 10,000 second. So, with this we will stop over here. In the next lectures we will be discussing about various other types of electrical, and even time will permit solar and nuclear rocket engines. Thank you very much.